Red River Basin or we call some basins. And the profile here, we can see that it manifests something like clearly velocity contrast at two sides of the region from Songma to Songda zone here. And from this kind of the profile, we can like confidently say about uh, the debate between the boundary of the Indo-China and South China. Also, we can see some like other velocity anomaly and the VPVS anomaly here maybe review or maybe tell us that this is the depth of something like the two-leg basin is one famous structure here, and also the depth of diagonal convoy that's related to this. From this kind of cross-section, I draw the conceptual model with some like discussion like this. First one, we think that plate boundary should be located on the region from the fold named 2, 3, and 4 here with the subducted slack westernly of the Indo-China to South China. Second one, we think that the Red River shear zone that's bound by the fold 5, 6, and 7 here may be unlikely like the lithospheric sky-slip structure. And another one now pay a lot of interest from the Vietnamese seismologist called Vinh Long. We think that it was a lithospheric structure. That's because it lithospheric structure, so it's subsequent of the Songma structure rather than the contemporary conjugate fold of the Red River shear zone at some like author things, geology or geology paper think about this. So here I will quickly mark out some conclusion for the first part. So the carefully take care about the catalogs. We already have the high quality catalog and improve the P-way velocity model from my advisor, my supervisors. And also the first time proposed the first S-way velocity model for Northern Vietnam, and thereby we have the VPVS ratio model. And from this model, we can see some insightful information for the architecture beneath Northern Vietnam by the plate boundary and also inside some major fault system. And I believe that the model can use to future study like the earthquake location or something, and even now the catalog can have a good input for other application like the seismic hazard assessment. After the successive of the first project, I jumped into the second project, that's joining with the three different kinds of data from the body weight teleseismic and the information from the ambient noise data. This data come from the linear array weak deployed in Vietnam from 2013-2018 by IES and IGP. And you can see here it has the north-east southwest changing with the interstation about 10 km and the total length around 240 km. However, after carefully checking the data, we revealed that the station VR12 here have some like amplitude issue. So unfortunately, we cannot use it for further analysis. Inside this, we have three kinds of data, and I will introduce you to the analysis to have this data step by step. The first one, we use a reservoir function techniques from teleseismic data to have the reservoir function that can sample the coastal techniques for Northern Vietnam. As you can see on the figure A here, we use around 4,000, nearly 4,300 global event with the epicentral distance from 30 to 90 degrees, and we only select the high signal to noise ratio data from those data sets. And using the reservoir function techniques, we can extract the green function for the reservoir function from each event to each station. And here is a example of the result station VR02. We for the data we apply something like Gaussian smoothing and also do some building for azimuthal. You can see the azimuthal coverage for those kind of the event, and also using some building for the range parameter. And after the stacking for each building here, we can see that we have the clear view for the first P way and also the side for the PS way, which can tell us about the relatively time from difference between the P way and S way. And from that, we can estimate the cluster thickness of the study area. We also can see some bad building here, bad stacking here. And those kind of the bad stacking will be like filtered out of the analysis. So here is a map of the output. You can see the peak for P here, peak for PSE here. And simply when we draw the line through the peaks with the time around 4.3 seconds, and using the simple equation from Zhu and Canori 2000, we can simply estimate the average cluster thickness along the linear array from around 34 something kilometer. Another kind of see more like easy imaging for the map. We can stack the normalized amplitude, and you can see here the red color variation here represents the cluster variation along the linear through of this. Note that from here we still have some uncertainty due to the missing data of this. Okay, this already. So the second and third data type, we like extract this in the information from the ambient noise post correlation that quantify on the ambient noise of the 4-year data. From here, I represent 4 components of the CCF function, post correlation function. And we can clearly see some move out, some surface wave content here. And if we check through this move out with the distance of the array around 240 kilometers and the time here around 80, so we can simply estimate the railway velocity, average velocity of this region around 3 kilometers per second. However, to detailedly check for each station, we need higher techniques. So this technique, we apply the technique called the array beamforming from Ross and Thomas 2002. This kind of figure represents the conceptual definition of this. We can cheat one station at the visual source and one root station at the receiver array. And from the array center, we can define the window like this and cut through of the array member. And afterwards, during the slowness, we search for the slowness from 0 to 3 or 1 based on our definition, and with different azimuthal direction, we can see those data and stack into the final chain like this. And this final chain afterward, we can construct the beamforming power diagram like this. And you can see here the example that the red color will show the area with the highest power. So here is a example I process is for linear array. You can see the diagram here. And because we already know the visual source and the station, so we can know the azimuth, back azimuth of this. So we simply research along this back azimuth and find the highest peak along this. This one extracts from this kind of azimuthal, and you can see here we can have the peak for the peak slowness here, and after that we can translate it into the velocity. And the figure on the right hand side shows the result, the output result of the beamforming for whole the array member. And because this one we assume that for the stable result, so we need at least 3 members inside the receiver array. That's why we're missing something like the data, at least for the two flanks of the array. based on this input map here, after that we did some QC about the data. You can see here only the station with well distribution of the peak like this. For example, this one is an example for the station VR 11 at period of measurement around 15 seconds. So we have a different peak distribution like this, and we define that something like consistent and consistent of the distribution and well distribution. And also from the data and number of measurement and also the standard deviation based on this distribution, we use some criteria to remove some unreliable data by the criteria of uncertainty less than 10%, and also number of observation here should be larger than 4. Another kind of data we can extract from cross correlation data we call the railway ellipticity. The railway ellipticity is a ratio between the horizontal and vertical direction. From here, we can achieve this by calculate the ratio between the radio, the ZR over ZZ component combined with R and ZR component for the short station. Because inside the cross correlation, we have the for example here the ZR. The R here is a component from the source station, and the Z here is a signal from the receiver. So we have the couple for the source and receiver. So S over V for the source we will be using like this, and for vice versa for receiver we have the equation for the like this. And based on the time series of the cross correlation, we can like checking the elliptic like relative practical motion of every result here like this to checking the quality of the measurement. And the final map of this analysis, in this one the output, not the final, of the map along average something like this. And we also apply some QC for it, like another kind of value distribution. And also we use a criteria for uncertainty less than 10% and number of observations 8, because we have the forward and backward for the SOV, so this one maybe 2 times higher than the threshold for the VP calculation. And you can see here the map on the right hand side, so the output result for SOV and also some other index like the standard deviation, number of observation, and also the uncertainty calculated from those data. When we have 3 kinds of data, so the question is how can we join it together? Because it has a different characteristic. So we adopt the method called the Markov chain Monte Carlo inversion from the Fanchi Lin group in University of Utah, USA. Less easy imaging about this. From this kind of the 1D model, we can like translate it into the subset of parameter. Here I use 14 different parameters to fully characterize for this kind of station. And from those parameters, we can use it to forward into the data for the real function for phase velocity and also S over V. And it's linked together by the likelihood function. I will detailedly talk about this later. After we have a satisfied subset of the data and the model, the parameter here will be generated into another subset of the parameter based on the Bayesian, we call the Bayesian generation, and check again for some criteria reconstruct into the model and quality control for this. And if the model is satisfying our criteria, it will accept, otherwise it will throw out. And finally, we have some like subset of output model. You can see for the gray line here. Maybe it's not quite clear, but we still can see some like darker color for the background. And from this kind of output population, we can average into the final model. And from this, we also have other assessment for this. So more detail for about the Markov chain Monte Carlo imaging, thus we our target something like the distribution of we call probability function for big data here. It will likelihood of the link of the probability density function. This one generate this one helped by the Bayesian generation, and here we also have likelihood functions. It quantifies the misfit between the synthetic data, forward data, and the observation data, and based on the link like this, and do some. If we simply do like this, it calls a random walk Monte Carlo inversion. So it easily fall out into the local minima. So the use of the Markov chain into here will let us to make the generation here jump into different direction. So it will now form the nonlinear problem because we jump with different directions. So we have the highly dimensional nonlinear problem. The likelihood function here linked together using the code function LM with the midfit of the data X and like this. And from current study, I use relative weighting term to link together. You can see here the surface way linked with the reservoir function. And surface way just contributed by the dispersion and also the ellipticity and reservoir function here. Finally, the final links of those following this equation. And for each model M, we have one choice value like this. And based on this, we can select all of the output population. From here, we can clearly see that MCMC is very effectively joint inversion for multiple type of the data. Here, I introduce to you some one example from the output model. This one is a zoom out just only for 5 km up. So here's the data from phase velocity. Here we can see we have the absolute value. So this kind of phase velocity can contain the absolute value of the output model. Also, the S over V here can sample the shallow path of this. Reservoir function will contribute to whole of the model during the long lasting data. And more clearly about the contribution of VP phase velocity and ellipticity, we can see, oh sorry, it's this one for phase velocity and this one for ellipticity sensitive. No, it's already high. So based on this, we can clearly see that with different kind of period here, it will sample different depth for the 1D model. For example, this one you can see the data here around 30 seconds and for phase velocity and 19 seconds for the S over V. So based on this kind of sensitivity kernel, we can obviously see that the S over V will constrain to the depth maximum around 10 km here. And for this one, it can constrain to the depth maximum to the 25 km. So the rest of the data will be contained by the river function. And you can see the peak here for the river function somehow can characterize the jump of velocity model between the crustal and mantle. However, as you can see, the distribution of the ray here is more like curiously due to this part below the 25 km. It's more and it has a higher uncertainty due to that driven by only single child data. And based on this, we also can calculate the standard deviation for each point of the model. And maybe it's not clear, but you can see the purple line here. I have also have the arrow bar. This one represents the standard deviation of each point inside the model. And this one also has the trade-off between the velocity and layer thickness. This one, this gray line separate into many like small sub-layer. So the velocity variation and also depth variation will contain by the livelihood of those data. That's why the final model I need to like resample in x 5 kilometer. The y dot here will represent the average value for whole of the value along this depth. And from the standard deviation here, finally we can like stack into the figure of the model uncertainty. You can see here most of the uncertainty located on the sediment layer, also the two flanks of the image, a little bit higher on this area, and for the mantle, because it mainly contained by visual function, so it gives a higher uncertainty than the cluster. Also, because as I mentioned previously, I use 40 parameter to characterize the model. Inside this have one parameter to quantify the cluster variation. So from those kind of distribution, we also have the cluster thickness with this, the uncertainty here. And here is my result along the array. We can see from the right to left here, where I also point out some location of the major fold for this area. Also the index of the station with no data, I have full data, and missing some kind of data or insufficient data. Along this, I also using two equations from previous studies, such as simple estimate the cluster variation from first one, we call IRI isostasticity from topographic model, and represent the thickness of the cluster. And another measurement we take from Google anomaly and using the linear transfer equation from Leonardo 2000. Sorry, this year should be 2030. And right now I will give you some interpretation about this. The first one, we access about the thickness of the cluster. From east to west here, we can see that the cluster variation along the arrays have the range from around 30 km to 35 km. And we can clearly see the variation here can characterize in three different domains. I separate here like the northwestern side, the shear zone area, and northeastern side shear zone and northwestern side. And those variations show good agreement with two previous study using the transfer equation. Some of the velocity tell us that maybe the sediment cover along the array will have the depth from 1 to 2 km. However, I need to mention that we have the high uncertainty on the sediment layer. And here we can see the strongest heterogeneity observed in mid to lower crust, revealed by the mixing of the high-low and high-low velocity here. Okay, and right now, other interpretation about this. Let's take a look about this. We can see the velocity contrast along this array, and it limits the region from the sunlight and sunlight fold. And XMS here represent the sunlight searcher on the western side. So we think this one may be linked to the boundary between the Indochina and South China, which well agreement with the past one tomographic model. And here we can point out some kind of low velocity zone beneath this region on the mid to lower crust. This may be linked to possible of the crustal channel flow. That's widely reviewed for this area and also southern China. And here we can see the very high velocity zone beneath the shear zone here. And with the upper one, I refer it to the metamorphic core of the region. And for lower crust pass, maybe it's linked to cluster underplating or the lower crust crystallization of the material. all of this feature may be associated with the inhumation process along the sky slip shear zone. Also here I introduce to you the consistent of two projects. You can see the lower panel here is exact from the same linear along the linear from my tomographic model as well, and the upper one the current study, and you can see some like even the S-way from tomography, travel time tomography with a lower resolution. However, it shows some consistent. For example, we can see maybe the manifest of the lithospheric velocity contrast here. Also, some high velocity zone below the shear zone, beneath the shear zone, and we can see some upwelling here of the velocity, some growing of the velocity, and also some low velocity zone here and here. It's a little bit sweet, maybe maybe can explain by the different kind of the grid of the S-way model. So here with the model like this, with the high resolution model like this, I go to some conclusion about from this model. First one, the cluster thickness along across the radial shear zone along the arrays can relatively separate into three domains like uniform, eastern, shallower on the shear zone, and more complicated on the western side, which related to the coastal variation nearby the tectonic boundary. And coastal heterogeneity across the profiles are mostly concentrated on the middle to lower crust. It may reflect some like the complex tectonomagmatic process, and it may represent the coastal channel flow of this area. And the observed high velocity anomaly beneath the shear zone have interpreted that is manifest of the metamorphic core on the upper crust and magmatic underplane or crystallization on the lower crust. This feature may be linked to the exhumation processes of long-term deformation along the major shear zone. And finally, the conclusion from two projects have four conclusions like this. Because I mentioned a few times already, so I will like place this here. And my last slide will be some sharing with you my future potential and my future work. First thing, I will, for the near future, I will using the data from the teleseismic to have the dispersion curve from both surface wave velocity and also ellipticity to fill up the data for the longer period to sample to to the mantle. And long-term study may be based on the successive of the linear array. I will open it into 3D because right now in Vietnam the seismic station is growing up, so we can use this data for further analysis. And also right now we just using the data from all these seismological observation. We can think about the integrated other kind like the gravity or magnetic field. Sorry. And based on the subset of the phase I have for the first project, maybe I can change some deep learning model to automatically process for my organization in the near future. And thank you everyone for attention to my presentation.
So any question or comment, especially for the PhD student? No? Yeah, maybe the committee member can answer the question. I guess so, the first one I would like to invite Sean. You give the first.
Okay. You really do a lot of work to finish your PhD thesis, and also show some very nice results. But I have some questions about your some results. The first one is you just to do some data processing to increase some catalog, right?
Yes.
And how about the increase the catalog? For example, the magnitude distribution for the seismicity distribution. I cannot see anything about this information.
Oh.
That's the first one.
Yes.
And the second is how to pick the PG or PM in your waveform.
Yes.
Because you also don't mention about this, how to pick this, and I don't know. You use some or some the tools to search this space. And the third is for your some profiles. For example, the S-weather velocity profile, you just have the 3 profile. But I didn't see any seismicity being plugged on this profile because I want to see if this determining feature may be related to the seismicity.
Yes.
Okay. And I also see you have some comparison to the 2D profile for the linear array with the many colors approach and your S-weather velocity compared with this, but it seems it's quite different.
Yeah.
Please explain the differences.
Okay.
Okay, that's the first, the 4 questions.
Okay. So we will go for the first question based on the magnitude analysis. In fact, I already think about the magnitude analysis during this kind of analysis. The figure here also not show the magnitude differences, but I have the figure for this one. Okay. Based on this work, you can see a little bit different on the magnitude distribution here. However, based on the issue of the catalog in northern Vietnam, mostly it's fall outside of the domestic seismic station. So and you know that we use the ML's only effectiveness for the epicentral distance, say less than 200 kilometer or maybe a little bit higher to 350 something. However, if we go further, it's that cost is more high uncertainty. So based on the framework of this kind of the catalog, I tend to temporarily keep the magnitude value at the input. In fact, the number increment here, because we use 5 station record for each earthquake only. And when we add more stations, so we have more data from those here based on the section criteria. I think the earthquake catalog now is really good for distribution, but for the magnitude analysis, we should a little bit need a few steps to analyze this. About the second one, sorry, what is it? The second question.
Second question.
Yeah,
Okay.
sorry.
The second question is for how to pick
Oh,
the PG.
okay.
Yeah.
Sorry, I will jump now because I prepare the supplementary a lot.
Yeah, strong. Maybe one question, one answer.
Okay.
Yes.
Otherwise, you cannot remember so much.
So, sorry, I did not mention previously, but inside the figure I showed you, I already rotate 3 component seismogram into the ZRT. So this one is a synthetic waveform from those group. We can clearly see that when we first PUA, it's easy to pick on the Z component, right? Because we have some clear peak here and it's strongly reflected by the gravitational force or something. So for the first arrival, they are easy to pick. For the two of these, we have two criteria to pick this. First one is based on the amplitude on the Z component.
So this one, do you use the Topi to check?
I also use Topi to check this.
Yeah, so is it similar?
It's almost similar, and you can see the separation. However, here I have one, I need to mention that maybe the PZ and PMP is too close. So here I assume that PMP and PZ almost the same location. Because when we go to further distance, PZ and PMP will be like easy separation. But for close distance, I assume that is PZ.
Yes.
And consider the, maybe the overlap happen, but I consider that's a error inside the PQ. And when we rotate the R and T component, you can easily see some line manifest of the SN and SE on those components. So I use this to quantify both on the theoretical travel diagram and also based on the amplitude content. Yeah.
Okay. The third one, do you remember this?
Sorry, I'm too nervous.
The third one is because for a why you don't add some seismology to your profile.
Okay. Maybe. See this. In fact, I have the seismicity. You can see on the purple circle here. But it's not too much. Yeah. If you see the distribution here and it goes here, and I just penetrate the seismicity.
Why don't you just follow the SOMA fault? Because you know the many seismicity occurred
Yes.
along this fault.
But
Why you use the lighter fewer the seismicity you do rather.
in fact, here because the purpose of the paper, we something try to have a good story about maybe the story of the Red River, which most of the people believe that is the boundary, right? And if we draw the profile here, something it may not cause the differences along this. So I tend to cut through of this to have to see the clearly like velocity contrast as well as the VPVS here. And yeah, maybe have other kinds of good represent about this. However, the answer for those questions, that's yeah, we do have some seismicity here. But
So that's fewer.
yeah, that's few. And the final one that I remember.
Yeah.
Yeah, so we jump to very last slide.
Okay. Just the start in page 25.
Okay, 25.
This one you use the receiver function to,
Yes.
to define the cluster thickness.
Yes.
That line is just the
simple line, yeah.
But why you don't use the CCP?
In fact,
Because just you use the receiver function.
that's a good idea, and I think I can use this one of the criteria to check my result. Because right now, the CCP is something that you simply average the P-way input, right? But the P-way can be changed along the array because it's complicated of the area. So I think the CCP also good to effective to quantify the variation. But based on current study, we want to see the variation of the cluster also, and it contributes different kinds of data. So, and the input of those kinds of data didn't use like another analysis like HK stacking to find the thickness. We just simply like based on the parameter to translate into the forward receiver function and find fitting. So it's more straightforward.
So what about this for the thickness of the arsenic?
Sorry.
The arsenic of the thickness for the crust thickness.
This one is not. I just simply translate from.
It just the translate.
Yeah, from to help you to have the pre-imaginary about the final one, and we simply can. Sometimes if we have no time, we have some result, we can.
Because I think that you just use many telesearch in the event to search the crustal thickness. So I think maybe you have some sensitivity analysis for the or interface.
In fact, my senior already did it, so I not tend to fall into his land. My senior former professor one student already did the result for whose array from the CCP.
Okay.
And have one more question.
Yeah. For the KG 39 and the 43.
Oh,
39.
39, sorry.
39, maybe anyone will ask you. Yeah. The 39 and the 43, just you describe the 2D profile for the use the many color to attain the final
Yes.
the final structure. But you compare it with the 43, just the S
Yeah,
way.
maybe
the
a 43 is
pathway.
better.
Tomography.
Yes.
Yeah. So do you think this is similar?
Absolutely no.
No. Yeah.
Honestly, but
you see just describe this is similar. So I have confused about it.
yes, you completely right. Because here's a velocity range, here just really small scale.
Yeah.
And I also deeply think about this, and maybe it's due to the damping and smoothing during the tomographic inversion during the
You just
processes.
use the same color range.
In fact, we have some figure to compare this, but this one different color range. You can see here the value of absolute range here, and this one from 2 to 4.5. Yeah.
So I think maybe you must have used the same color range together.
I already use this, but it looks so terrible, so incomparable. But you can see here, even this one have a smaller variation range, but inside our result, the pattern, it may have some similarity. And this side and also the location maybe is different, because in the tomographic we separate the crust into for upper crust this is 5 km and after that 10 km, so resolution and the location may be shifting, and yeah, the magnitude different.
Yeah, but for the VS triple tandem tomography, you just can see for the lower cluster flow. It's just to show the low graph.
This one?
Yeah.
Maybe because I cut here from 10 to 20, so you know the conception of this image, you have the cross ray, right? So it's variation, and the size of the model may be a little bit high. It's got something when we translate into the figure like this. So I think here it should be similar, but shifting a little bit.
Okay.
Yeah. I also have a comment about these two results. Due to you cannot say that a product use the same scale is terrible. No, you cannot say that. You use two different approach, got the velocity. Actually, for the velocity structure, simply just one. You need to have put into here, just like you have essays, you got the two results. You need to discuss, put into the discussion. At the final, the discussion why you got to expand, maybe method problem, data problem, you got a different result. Not to say why you product use the same color product is terrible. That I cannot accept it. So I guess this should put into the discussion. Yes. Okay. So go ahead.
Yeah, I just finished the first stage.
Yeah.
Yeah, next one.
So on.
Okay. First of all, I'm amazed that you illustrate the detail of the seismotectonics in the northern Yunnan by considering tomography, by considering some of the detail of the seismic images through this kind of the profile. So as you present, generally you demonstrate the result or outcomes from two projects. That is very, very common in the PhD thesis because we expect during your very long journey of the PhD, usually not only you yourself but also your supervisors expect you could have varieties of outcomes. So that's the reason why in many PhD theses they have the publish several papers or at least involve several projects, which is sometimes a little bit slightly different between each other. So you have very good strategy that you put the chapter 4 and the chapter 5 for your two projects. But if we are talking about the framework or the outlines of a project, outlines of a thesis or a paper, usually we will say we first have an introduction, methodology or data, and the result, and the discussion conclusion. And in